So this meeting is about drive and so on. So I'll try to connect to something. I don't really work on drive-driven systems, but this talk will have some connection to drives and so on, in the sense that we'll try to look for something like the AC response of what I call the Chklovskii-Halperin Quantum Hall step-up transformer. So you're talking of a transformer. So what you want to do is you want to use the quantum Hall state as a possibility to kind of use it as a small micro-sized transformer. And I think Halperin and Chklovskii came up with this idea in 1996, how to use them theoretically in the DC limit. And what I intend to finally show you is that it can be extended to the AC limit, and the AC response is actually stronger than the DC response, in the sense that the gain is actually larger in the AC response as opposed to the DC response. And to begin with, let me give you the answer. And it turns out that this enhanced response is coming from the fact that when you have AC currents, you also have displacement current associated with the circuit, and these displacement current can lead to responses which are larger than the DC response limit. So that's the talk all about, and I'll give you a history of how we kind of worked with this subject. Here are my collaborators. So Amulya Ratnakar and Sampurna Karmakar are PhD students working with me. Kishore Iyer is a collaborator. Arijit Shah, Amit Agarwal, Sumati is here, and Diptiman is also here. So these are collaborators. So let's start with a very simple picture. So this is a picture of dissipation in a one-dimensional channel. So if you consider a one-dimensional channel and you have two reservoirs, one maintained at chemical potential mu1, another maintained at chemical potential mu2, and let's assume for the moment that it is at 0 temperature, and you have a barrier in between which has a transmission probability T and a reflection probability R, then if you consider this situation and now switch on a magnetic field to simplify matters so that it goes to the quantum Hall limit, such that the right movers kind of physically separate out from the left movers, so that you get a picture which starts looking like this. And in this scenario, because this response is separated out, the injection channel and the outgoing channel, you can have really neat measurements. So that's the whole motivation of taking this 1D channel and kind of separating it out into right movers and left movers, and putting contacts on them at chemical potential mu1 and mu2, and then asking this question, how much is the dissipation? So you can easily convince yourself that if the transmission and reflection probabilities are T and R, the outgoing, so the imposed distribution function is this, and the outgoing distribution function will be, say, a double step function, where in the bias window you are filled with a probability T and not 1, and similarly in the reflected beam in the bias window you're kind of filled with the probability R. Now what you can do is go ahead and replace this double step beam into an equilibrated beam, and that tells you how much maximum amount of work you can take out with this double step beam if you bring it back again to 0 temperature. And these are fermions, so you cannot do anything better than that. So if you start with double step, the best you can do is bring it back to this new chemical potential filled up to T times mu1 minus mu2, and this will release certain amount of energy, right? And it's also tell you that if you make a measurement, so in a sense that if you go back and if you could make a measurement of a local chemical potential here, which in the quantum Hall experiments we can do, you should measure a chemical potential which is T times mu1 minus mu2. Yeah, please go ahead. Yes, that's exactly the local, after the reflection or the transmission has happened, the local chemical potential on the edge is T times mu1 minus mu2 and R times mu1 minus mu2. That's the local chemical potential, exactly. And that's associated with a certain amount of dissipation, which you can calculate simply by calculating the energy content of this double step beam and this distribution function. That gives you the dissipation. So if you add these two energy up, what you're going to get is nothing but I squared R. It should just equals to I squared R. That makes perfect sense, right? So you can now extend this formulation, and if you have n terminal setup, if you imagine that there are n incoming channels and n outgoing channels, then you can impose a voltage on each of these incoming channels, which I call V1, V2, Vn, and you can also you can assume that given the scattering matrix of the junction, you will have voltages for also the outgoing channel. So you can vectorize the whole problem such that there is an input vector, which is the input voltage column, and then there is an output vector, which is the output voltage column, right? And now you can ask this question again, that how much is the power dissipation? The power dissipation in this case can be written down in a nice form. So maybe I just make a statement here. This is just the generalization of v squared over r, where you can see that v vector dot v times g is the conductance, 1 over g is the resistance. So that's just v squared over r, and that's what the power is. So we are taking the input power, we are taking the output power, we are taking a difference of the two, and if you do that, essentially the expression for the power dissipation turns out to be something like G over 2, the vector V input, identity minus m dagger m times V output, where the M matrix is a matrix which connects the input voltage vector to the output voltage, the output voltage vector to the input voltage vector, okay? And how do you calculate it, at least for free fermions? For free fermions, it's very simple. If you have the scattering matrix at the junction, you just mod square that quantity, and those mod square essentially sit into the matrix element of these guys, giving you the matrix M. So that's what it is, and now we can ask an easy question that when is the dissipation maximum and when is the dissipation minimum? What is the M matrix for which the dissipation is maximum, given a particular voltage configuration, and for which configuration is it minimum? So to answer that question, that's also an easy way of answering that question. What you have to look for is this thing, that given a M matrix, given a way the junction has been shouldered, right, what you need to look for is a vector which for the M dagger M matrix has an eigenvalue either 0 or 1. If it has an eigenvalue 1, 1 minus 1 is 0, so you have no dissipation. If it happens to be 0, then you have maximum dissipation, right? So now this M matrix, so I think the point to realize is that this M matrix carries information about how the current splits. It really doesn't tell you, so this is a more general, so this formula here really doesn't care if you have a electron-like quasi-particle or a fractionally charged quasi-particle. It really doesn't care about that. If it is a Fermi liquid or a non-Fermi liquid carrying the current, it's not something which goes into this formula. It is independent of that, which basically means it's a general formulation, right? It doesn't care about what your quasi-particles are. So if you are in the fractional quantum Hall regime, these will be really fractionally charged quasi-particle which will be carrying the current. Now, which means that this formulation, when I'm looking for an M matrix which gives me 0 dissipation, is an interesting question, because in this question, of course, we'll answer for which scattering matrices, if I take a free fermion picture, I'll have no dissipation. That's actually a boring answer. That's not the interesting thing, but I will also get answers for those situations in which it's not a simple Fermi liquid, but it is a Luttinger liquid, and in that case it has fractionally charged quasi-particle, and it will give me the fixed points of the theory, which are essentially conformally invariant points, right? So this is one route to finding out that if I take all these interacting edges and knot them together at a point, then if I want to know what is the description that this defines a non-dissipative fixed point, one route to get there is to smartly construct this M matrix with appropriate constraints and look for situations where they give rise to no dissipation. Okay? All this is 0 temperature. There is no temperature right now. It's the description of the field theory, and then you can plug in temperature and calculate things. How it equilibrates is something then you have to plug in. See, right now what I'm giving you is like if I give you that, there are 3 wires and their S matrix connects this way, that's like the microscopic description. Then you want to switch on temperature and not, will decide how scattering happens and how equilibration happens and so on, right? That's the different details. I'm giving you the spectrum here. I'm giving you the field theory. Once the field theory is in place, you can do it at finite temperature or 0 temperature. It's a matter of choice.
What is the mechanism for
I have not assumed any mechanism for equilibration. I have assumed complete equilibration and asked this question that if that happens, how much energy will be released? So that's the best that can happen. That's the bound if you wish. Okay. So this was, and I think we formulated this question in this paper, and then regarding dissipation, and recently we also extended it, and we had some kind of a out of equilibrium fluctuation dissipation relation, which basically means that if you know how to calculate the dissipation, you should also be able to calculate the noise that you can measure in each of the terminals. Essentially, you are injecting current and it's scattering at the junction and going out. When it's going out, it's going to generate fluctuation because the process in which the current is carried is probabilistic, in the sense that if you have a barrier, with a certain probability, the electron passes through, and with a certain probability, it reflects back. So essentially, if I zoom in and look at the current, of course, the current will have an average expectation value. The current operator will have an average expectation value, which is proportional to the transmission probability. But there will be a standard deviation of the current, which is the fluctuation of the current, which we call noise, right? And that has to do with the fact that every electron has a possibility to either go forward or go backward. Now, these fluctuating objects essentially generates a non-trivial distribution function. And these non-trivial distribution function essentially finally equilibrates to give you dissipation. So it's natural to think that you will have a relation between the total amount of power that you can dissipate, the maximum amount of power that you can dissipate, and the maximum amount of noise in the charge current which is flowing out of the circuit. And we could show that indeed there is a relation in this paper between the total noise and the total dissipation in such circuits. Is also zero temperature, yeah. It's a zero temperature charge noise. Yeah. No, no temperature. You can ask this question that once this dissipation happens, then how much, see in all this mesoscopic phenomena, the dissipation actually happens in the lead, not in the system, if it is in the ballistic regime. So you can ask this question that if the dissipation happens in the lead, because of your non-equilibrium distribution, how much elevation of temperature will happen in the lead in the long time limit? That's a valid question to ask, but over the DC time scale, over the time of flight over which the electron is running through the circuit, you can ask a different question, which is this one. Everman, okay, we can do it in person. I don't have it here, but it's actually reported in this paper. Okay, so let's move ahead. So what you realize is, if you write a M matrix at least for a 2x2 case, where you have a two-wire junction, then you can convince yourself that both for interacting and free theory, the only possibilities are having zeros and ones in this matrix. Essentially means that either you have perfect reflection or perfect transmission, and these are the only trivial or the non-trivial fixed points of the theory. And this is consistent with bosonization. If any of you know bosonization, you will know that this corresponds to a simple CFT, C equals to 1 CFT, which if you think of boundary operators in that CFT, then the boundary conditions, the non-trivial boundary conditions you can get there is only two, either the Neumann or the Dirichlet boundary condition, and they essentially corresponds to only two possibilities, which is perfect reflection or perfect transmission. So nothing interesting. But it turns out that as you start looking at the 3x3 case, you can parameterize the M matrix in a certain way, and this parameterization essentially tells you that there are many, many points, actually most of the point in this parameterization, which tells you that it's dissipation less, but it also tells you that nothing of a free electron theory can mimic any of these matrices. So there is a whole class of matrices, actually one parameter family of matrices. If you scan the parameter space, most of the points are actually a non-Fermi liquid. Only certain few number of finite points actually is describable in terms of Fermi liquid. It basically means if you try to write them as mod square quantity of some scattering matrix which is unitary, you will fail to do so. Okay? So they are not describable in terms of Fermi liquids. So it's essentially telling you that these are fixed points, non-trivial fixed points of a non-Fermi liquid theory. And in recent times, we of course did a lot of work in this area long time back. You can see that it started from my PhD period, 2004. And then there was a very nice review article also by Affleck, Shimon, and Oshikawa on this. And then we started revisiting this problem because there are certain questions which you could not answer then. And I'll tell you about a few of them. One of the questions which we ask is that if you have such non-trivial fixed point, what characterizes them? What is strange about them? You can start looking at these matrices and convince yourself that if these are the elements of the matrices, there is a possibility that these elements can go negative. As I told you, in case of free fermion theory, these are mod square of certain scattering matrix element. So of course, mod square of scattering matrix element cannot be negative. Whenever there is a negative element, it's telling you something interesting is going on. It's telling you that certain kind of processes is going on, which is more like the Andreev reflection process. if for those of you who know the Anrave reflection process is just a process in which you have, on one side you have a free fermion theory, on the other side you have a superconductor, and you have a junction between the two, and if you send off an excited electron above the Fermi C, once it reaches the junction, of course, an excited electron cannot enter the superconductor because there is no density of states for it. So it has to pair up with another electron and then bounce back as a whole while a Cooper pair enters the superconductor. It is analogous to that in absence of superconductivity. It's telling you that you have multi-particle scattering going on such that both electrons and hole participates in the process, in the sense that if you have incident electron, then what can bounce back is actually a hole, and on the other side, what goes off is something which is more than an electron. So you send off an electronic current of a certain amplitude, and what transmits is current more than what you send, but what reflects back are holes. So total current is conserved, but these multi-particle scattering processes due to interaction actually allows for such scattering matrices. These are not scattering matrices, they're current splitting matrices. And this is purely due to correlations. And that's exactly is at the heart of what makes the physics of transformers happen. So when Chklovskii and Halperin looked at this problem, they essentially utilized this point that such possibilities exist. Yeah, please go ahead. Yes, I'll exactly answer that question. Yeah, absolutely. So one simple example I will show definitely in this case. That's the Chklovskii-Halperin case. But you can of course cook up something much more complicated, which are coming out of these 3x3 matrices. Okay, so here are examples where you can see that this is an example. Again, these are all cases where the Fermi liquid theory and the non-Fermi liquid theory completely matches, while of course the conductance is very, very different in the two cases. You can see this is a nice one where this is a chiral, what you call a chiral fixed point, where there's a perfect transmission between 1 and 2, 2 and 3, and 3 and 4. This is a disconnected fixed point where everything is reflecting back. If you come from 1, you go back to 1. If you come from 2, you go back to 2. You come from 3, you go back to 3, right? So these are cases where the Fermi liquid theory and the non-Fermi liquid theory matches with each other and remains dissipationless, but there are all other points which are not comprising of zeros and ones, they will essentially correspond to non-Fermi liquid theories. Okay, so with that, let's move ahead. So let's ask this question: what is it that we can calculate or measure in this theory, which can be interesting and give an indication that something strange is going on? All these whole reflections are going on. So what we looked at is something called the tunneling density of states. What is tunneling density of states? So the idea is very simple. If you have a non-Fermi liquid theory, then it's telling you that if you have a piece of metal which is non-Fermi liquid and you bring in an electron and try to inject the electron into the system almost close to zero energy, then of course there are no such states in which you can inject the electron, which basically means if you perform an STM experiment and you look at the current as a function of voltage at the zero bias limit, you should see a strong conductance suppression, right? You should see what is called a zero bias anomaly. So essentially, if you look at the tunneling density of states, you will see that at least for Luttinger liquids, there is a suppression of tunneling density of states and it follows a characteristics power law. So there is this power law suppression of tunneling density of states as you go to zero energy, right? So we are essentially trying to look at that and ask this question, that is there anything strange about this fixed point which gives you a physics which is different than this, right? So is it possible that even if you would imagine that if you try to inject an electron, because it's a non-Fermi liquid, there are no electronic states very close to zero energy, an electron will be repelled, or you'll not be able to really inject the electron in, which means the current will be suppressed. Can it happen the other way around, that actually the current is welcome? Now, why is it that we are asking this question? We are asking this question from this intuition which you have from this paper from 1996. It's a paper by Rosario, Fazio and company, that what they showed is that if you have a superconductor and if you connect it to a Luttinger liquid, and then if you look at tunneling density of states in the vicinity of the superconductor, then you can show that at least within the coherence length, there is an enhancement of tunneling density of states. So if that is the case, you have an idea that if you bring in superconductivity, there's a possibility that rather than having a suppression, you will actually have an enhancement. But of course, we don't have superconductivity, but at the same time, we see that there are certain correlations which are mimicking superconductivity. The question would be that now if I calculate tunneling density of states, will I see that kind of an enhancement? And in 2009, we did this calculation together with Amit, Sumati and Diptiman, and actually saw this. we saw there was many of these fixed points which essentially had, as I said, these elements with negative sign in the M matrix, which essentially represented some kind of Andreev processes. We also saw an enhancement of tunneling density of states, which is very unusual of Latinger liquids. Now, we felt the following while we did the calculation. We felt that it is essential that that you have for the enhancement, you need at least a 3-wire junction, because a 2-wire junction seems to be boring in terms of field theory, because it only has the Dittlian and Neumann boundary condition, which corresponds to either complete transmission or complete reflection. So the minimum thing which you need for observing such a phenomena of enhancement of tunneling density of states is a 3-wire junction. Second thing which you observed is that these enhancements were always coupled to these fixed points, which really had this negative current coming out of it as you send off a positive current, right? These two looked like essential. And I was always curious that if it is indeed essential that we really need this physics. The other trouble which we had was that all the fixed points in which we saw this enhancement, it was RG unstable, in the sense that there were lots of relevant operator which could take you away, which basically telling you that if you perform an experiment, it's very unlikely that you'll see this physics unless you engineer it very well. So the question would be that, can I get rid of the first two conditions? That it is not a 3-wire junction, it's a simple 2-wire junction. It doesn't have any such Andreev phenomena going on, and it is a stable fixed point. Can I get this? If I can get these three going, then really it can be a good experimental proposal. So, and in fact, in this paper in 2021, we did a parameter scan and we introduced some kind of, we took a 2-wire junction and then we introduced all possible interactions. So we were having some limited number of interaction parameter in this problem. We essentially did a numerical analysis where we switched on all possible interactions which a system can afford to have in such situations in a quantum Hall context, and relooked at the problem, and we convinced ourselves numerically that actually all these conditions are not required. You can have a stable fixed point, it's not a problem. You can have tunneling density of states enhancement even for a 2-wire junction, that's also not a problem. And all the limitations which we had before, like we needed these negative reflections happening, even that is not necessary. We could actually show this. So that was something which we got in 2021. If you want to know more details about it, it's a bit of a numerical work. I can give you details. I cannot say that we have a very clear understanding of why this happens, why the field theory allows such a thing. But I would say that when we saw the first phenomena, we didn't have an understanding why that was happening. It was, what you could say is that it was always coupled to certain preconditions. And now what we observed is that those preconditions could be gotten rid of, and you can still get this physics that in a non-Fermi liquid, in a 2-wire junction, where there are only 2 kind of boundary condition, in presence of certain non-local interaction, you can have this enhancement of tunneling density of states. So now the next thing we were interested in, of course, to ask this question that if you put a superconductor, is it guaranteed that you always get an enhancement? And that was the study which we did in 2022. And this question has to do with our previous study, which I did with Sumati in 2008, around 2008, where he made an interesting observation that if you think of a superconducting junction of Latinger liquid, and if you think of a normal junction of Latinger liquid, what is the connection between the two? So the connection is that for those who are aware of bosonization and 1D phenomena, we know that the current and the density are conjugate variables in 1D, right? So current and density are essentially conjugate variables. So if you pin one of them, the uncertainty in other really blows up, right? So now if you think of superconductivity, so if you think of a superconducting wire, and if you think of a Latinger liquid wire, a one-dimensional interacting wire which ends up on a superconductor, then you can ask this question, what is the boundary condition, the effective boundary condition I can put on the field theory? And the correct boundary condition would be that the electronic density at the junction goes to 0, right? Because there are no electrons. Once you have superconductivity switched on, a gap's opened up, and there are no electrons. And this is a bosonic operator which corresponds to dou phi. The phi is a bosonic field which describes this physics. On the other hand, if you have a normal junction, which is a very large barrier, such that the electron comes in and completely reflects back, which I call a normal junction, in this case, what you have is essentially the current being 0. The density need not be 0. There can be background density. All one is saying is that if you look at the Fermi level and ask this question that what is the conductance in the vicinity of Fermi level, what you're saying is that whatever current you send in is completely reflecting back. So the boundary condition is that the current is equal to 0, which is corresponding to this conjugate field, which is the dot theta field, which has to kind of go to 0. So, and these two are conjugate observables. So essentially, what you can show is that there is in fact a duality between superconducting boundary conditions and normal boundary conditions. And this, by using these ideas, we kind of extended these ideas in this paper and showed that the enhancement of tunneling density of states may or may not have anything to do with superconductivity, depends on the details of what kind of dual theory it corresponds to in the normal junction case. You have both possibilities. So we kind of evaded all possible preconditions which we thought about were sacred. Right? Okay, let's move ahead. So now let's think of experiments. So now the question would be that if you are thinking of really superconductivity and quantum Hall effect together, it of course is kind of a bit confusing because superconductivity is something which is killed by large magnetic fields, and large magnetic fields are essential for quantum Hall effect. Now at least that things have changed, and this is a paper which we collaborated on with Anindya Das from IACS, that he actually could take a graphene sheet and overlay a superconductor on it, which was this strongly spin orbit coupled superconductor, and actually observe Andreev reflection happening, at least for integer filling fractions. Right? So it's not that it is completely impossible that you cannot put superconductivity and quantum Hall effect together. Now, there are now lots more experiments coming up. I think one of the very interesting experiment which came up recently is this experiment where there's a quantum point contact. This is in the context of two-dimensional electron gas, that you have a junction between n equals to 1/3 state and n equals to 1 state. I will tell you very soon why this has any connection to superconductivity. This is not an experiment about superconductivity, but this one is, which is a very recent paper and a very important progress, I would say, where essentially they had the quantum Hall state in graphene at n equals to 1/3, tuned to n equals to 1/3 state. And then there was a superconducting nose here, and they could send off current from here, electronic current, and actually take out whole current on the other side. So actually they could see Andreev reflection process while the filling fraction was 1/3, which basically means not only they saw Andreev reflection, they could see Andreev reflection of fractional charges. Right? So that's really, really interesting. So there has been enormous progress, and this one, then this comes back to Arnab's question. So what is a simple scenario where you will see something like Andreev kind of process? And this is the simple scenario where you will see Andreev kind of process. You have a quantum Hall effect which has a filling fraction 1. On the other side, you have a quantum Hall effect which has a filling fraction 1/3. There's a small quantum point contact here between which, so that the edge could talk to each other. And what they could see is some kind of negative current bouncing off from this junction. And why is that so? So let's ask this question, why is that so? And the argument is rather simple. So think of it this way, that imagine that I have a 1/3 quantum Hall effect on this side. I have an equals to 1 quantum Hall effect on this side. So this edge state is essentially described by a Fermi liquid, where this one is described by a Luttinger liquid. And now you have quasi-particles, and now think of a fractionally charged quasi-particle which is incident from this side. If it is incident from this side and I am in the strong coupling fixed point of this theory at this junction, then of course this electron, this quasi-electron, which has a charge of E/3, really cannot go to the other side, because the only guys which are allowed on the other side is electrons. So the thing which it can do is, there is some kind of sense of Fermi level for these fractionally charged quasi-particles also. These are called zero modes of the theory. So zero mode is filled up to certain Fermi level. What it could do, it could pair up with two more guys, two more fractionally charged quasi-particle below this Fermi level, and jump as an electron into the other side, in the n equals to 1 side, while a -2e star charge actually bounces off. Which basically means, if you have a quasi-particle mismatch on the two sides, then if you could tune yourself to an unstable fixed point, which is a strong coupling fixed point, it turns out that the strong coupling fixed point is an unstable fixed point. This was very well studied by these people in 1998, or I don't remember, or 1996. Shimon, Fredkin, and Slender actually looked at it quite pretty much in details, that what this strong coupling fixed point is, how unstable it is, and so on. But if you could somehow manage to get to this fixed point, then indeed you will see this negative reflection. Okay, so it's possible to have Andreev kind of processes once you have quasi-particle mismatch. So is this a reality? So let me skip this slide and tell you that this is the experiment and this is what we see. We actually see this, and so this was also at the heart of the proposal which was made by Chklovskii and Halperin to realize a transformer. So why is this a transformer? So maybe I am kind of switching back and forth. I'm sorry for that. So have a look at this situation. So what you have is that this is a typical Hall bar geometry. It's usually Hall bar geometry is a 6-terminal geometry. You have a source electrode, you have a drain electrode, which is grounded in this case. This has a voltage V, and then you have 4 voltage probes, which essentially do not carry any current and measure the local voltage. That's its job. Okay. So now it turns out that once you tune, so we know what is the strong coupling fixed point. If you tune the theory to the strong coupling fixed point at the junction and then start asking this question, what will these 4 voltage probes measure? It turns out that the voltage that, the Hall voltage, which means the transverse voltage, which means the V11 minus V10, this transverse voltage on the nu equals to 1 side will be V over 2. On the other hand, the transverse voltage on the 1/3 side will be 3V over 2. So you can clearly see there's an amplification of the Hall voltage across the QPC once you are in the strong coupling fixed point. What is V over 2 becomes 3V over 2. Okay? And that's at the heart of this proposal of this transformer action. Now you can go ahead and build a transformer. They had a proposal how to do that, but that's what is, so this is at least my interpretation of how to think about it. So, no, I do not have a V by 2. This is the source, and you impose a voltage V with respect to this ground. And it turns out that the Hall voltage on this side will be V over 2. So that depends on what is the boundary condition here. So that depends on the field theory. So the field theory tells you what is the strong coupling fixed point and how the current splits at this point. Once you know that, then you can calculate this. Yes. Current is conserved. It follows from Kirchhoff's law. There's no problem with that. Current is absolutely conserved. You can check that. It exactly follows a certain M matrix, which is a valid M matrix. There's something which you can check. This amplification is happening because of what I said. You see that this is what I said. That when you send in an electron, actually what goes back is minus of 2E. And you see that, so the voltage difference between them is kind of, if it was a normal reflection, imagine that I send in an electron, and an electron bounced off, then the voltage here and the voltage here, the local voltage here will be both positive.
So then that's what I was saying, the current above and current below, you will see different, right? This minus 2E.
Yeah, absolutely. So that's the point I'm trying to make. Now imagine that you take this current and convert this into a local voltage, you will get V1, and if there was a normal reflection, not Hall reflection, then you will get another voltage here, and both these voltages are positive, so difference of this positive voltage will be smaller than if you had a Hall bouncing off, and then you measure the local voltage here, so of course the voltage has increased. Right? The voltage difference has increased.
Voltage difference?
Yes. So that's exactly the Hall voltage. So there's an amplification of the Hall voltage, and it's a 3 times amplification. Okay, let's see what they see in the experiments. What they see in the experiment is the following. So as I said, that this fixed point is a strong coupling fixed point, which is also an unstable fixed point. So it basically means as you go to low energy or low voltages, you will go away from this physics. As you go to high energies, you will actually come back to this physics because it's an unstable fixed point, and you exactly see that. So what they see is that at large voltages, you're almost quantized, your amplification is quantized to 1.5, and as you come towards the 0 voltage limit, actually it starts flowing towards the disconnected fixed point and you see a dip. Okay? So the experiments seem to be really kind of following the theory. So now what we did, how much time do I have? 4 minutes, excellent, okay. So now what we did was we essentially considered a geometry, which I'm going, okay. which I'm not going to get into much of details, but what we have in mind is some kind of a bilayer geometry. So think of a graphene bilayer, which is both driven into the quantum Hall limit, such that there is first layer and its edge state, there's a second layer and its edge state. There's a QPC geometry being constructed by etching it and putting some gates here, such that there is some tunneling going on here, and then you can also have on top of it some gates which can kind of control the filling fraction on the top surface and the bottom surface. So that is the kind of setup which we are looking at, and then we calculate the AC conductance of this setup. So what we observe is the following. So now let me just in the passing, let me make this remark that you might think that how easy is it to calculate, it must be very easy to calculate AC conductance, but how easy is it to really measure AC conductance? So this is an example where they have done this experiment in the quantum Hall regime, where not only they can actually measure the complex, the amplitude of the complex complex response or complex conductance of the AC driving of the circuit, they can actually measure the argument of it and the phase of it, and both can be measured independently. So you can measure the conductance, the amplitude, the amplitude of the conductance. You can also measure the phase of the conductance. Okay? So this is absolutely within experimental reach. So I'm going to skip this. If time permits, I'll come back to it. So what is it that we observe? So, and how do you do the calculation? So the calculation is done in a simple fashion, that you know that the interacting electron theory actually maps to a free bosonic theory, and in the free bosonic theory, essentially what you can construct is wave packets, and you can start throwing wave packets at the system for which you want to calculate the conductance, and these are nothing but Gaussian wave packets which you send to the system, and then you look at how they are reflected and transmitted back. As you can see, even if I send off a positive wave packet, what I get in the reflection back is a train of small wave packets, which can be both negative and positive, which is telling you it can be both electron and hole. These are not electron and hole. What you send off is an object where this wave packet has a density which integrated over will give you exactly one electronic charge, and then you ask this question, how these charges as you send in, because electron is anyway not good for the particle, then it essentially fractionalizes, and what comes back in the reflection and transmission is just small fractions of this electron as either as holes or electrons on the two sides, right? Electron density and hole density. That's what you get. And now once you have figured these transmissions and reflections, once you figure them out, all you need to do is Fourier transform them back to the real space in the time domain. And once you are in the time domain, they essentially provide you the conductance of the circuit, right? So that's the simple exercise you need to do. And we do that, and the interesting answer which you observe is that the amplification factor is actually quantized, and it goes to square root 3. So the amplification was 1.5 as was seen in the experiment. So that was the DC bound, right? This is something I showed you. So the amplification was observed to be 1.5, and the question we asked is that once you go to the AC limit, is there a possibility that you actually push your amplification beyond this DC limit? And the intuition which drove us to do this is the fact that once you are in the AC limit, you essentially have displacement current. If you have displacement current, you don't need to have current conservation in the conventional sense, and because you have all these static charges now becoming dynamic and contributing to the conductance, you can get a conductance which is larger than the DC bound, given by the fixed point, unstable fixed point of the theory, and that's exactly what you observed. You observed that actually the new bound is square root 3. So that's an interesting scenario where this is possible. And let me just show you the plots and conclude. So this is the archive reference where this result is reported, and you can see that these are our first set of simulations where on the two sides of the junction we have both nu equals to 1 filling fraction on both sides of the junction, and you see that the conductance is quantized to 1, and then you switch on some more interactions but still keep the filling fraction same, and you see that still it's bounded by 1. And now what you do is, now you go to the interesting case where on one side you have nu equals to 1, on the other side you have nu equals to 1/3, and you immediately see that now the conductance peak starts as a function of frequency. There are resonant frequencies that they start kicking at 1.5. And it turns out that if you fine-tune your interaction parameters in an appropriate fashion, then the maximum bound you can get is essentially the square root 3. So this is the bound which you got, the DC bound. DC bound is obtained as long as your interaction are the standard interaction, which people consider in literature. But if you are in this bilayer system where the possibility of having more exotic interaction is switched on, then you see that actually the bound is not 1.5, it is square root 3. And this jump from 1.5 to square root 3 is exactly something which you can show is coming from the displacement current. So with that, I would like to stop and take questions.
Junction?
See, the inductance is kind of inbuilt in the sense that this is something I hid under the carpet. So when I'm considering this geometry, I have density-density interaction between all the edges, all possible density-density interaction. And each of this density-density interaction, you can think of it as a combination of a capacitor and an inductor. So you can model it that way. Actually, you can show that these density-density interaction can be recasted as an effective circuit where there is a finite inductance and a finite capacitance. But there is no resistance. That's the thing which is not there.
No, so I'm saying for DC that LC circuit is not there, or how?
Yeah, it is there. It is there, but it's not. It's not. You see, it's contributing, but how should I say? It doesn't participate as far as the displacement currents are concerned. Right? The interesting physics of displacement current gets activated only when you go to the AC limit. There are two things here. One thing is the physics of fixed points, which is a field theory boundary condition. So on top, there are two things which we have done. We have imposed a certain kind of boundary condition exactly on the tip, which has to do with this strong coupling fixed point, which is coming from the field theory. On top of it, we have also imposed all possible density-density interaction in this area, which are like switching on inductance and capacitances on top of this boundary condition. So there's an interplay of this boundary condition, which is coming from the field theory, which is a strong coupling fixed point, and these inductances and the capacitances. So if you have the right interplay, then you see that you get a very large enhancement.
You had a picture where there are a lot of little pieces of things coming back after reflection.
Yeah.
Right,
yes.
This one. So each of these, if you integrate over them, is some definite fraction of the
Yes,
charge?
yes, yes.
Okay.
We actually even tried doing some statistical analysis of it.
Right.
And there was nothing much interesting there, but we are still thinking about it, that can we get an interesting time series out of it.
But they're individually quantized.
Yeah, they're individually, not really, no, when you integrate over, of course, when I do to charge conservation, you see that if I know that my pulse, the total charge for the pulse is 1 unit, then when I look at the total integrated, transmitted and reflected charge, it will sum up to 1, of course.
Yeah, but the separate ones.
Separate ones are not quantized, they are just arbitrary numbers. Yeah. But given the boundary condition, they are fixed. It's not probable, it's still deterministic in the sense that it's still classical in some sense, because I'm at the fixed point, so there are no fluctuations, and the strain is completely predetermined. There's nothing probabilistic about it. I think probably that's what you are hinting at. If it was a non-interacting theory, if it is a free fermion theory, of course these pulses will be really fluctuating pulses. They're occupied with certain probability and unoccupied with certain probability. These are completely deterministic. I send a density pulse and it fragments exactly this way every time I perform the experiment. So every time I send this guy, so you can ask this question, every time I send a pulse, I exactly get the same copy each time. But this is not true with the electron being incident in a Fermi liquid theory, right? It will be probabilistic. Sometimes it will transmit, sometimes it will reflect. If I take the full statistical ensemble average, then I will see that it will converge onto the transmission probability and the reflection probability, and it will be noisy. The current will have fluctuations. But here, the fluctuations are also deterministic in some sense, in time.
Yeah, but what I'm worried about is, suppose you only capture one of them.
Yes.
So then you've got some fraction of an electron, which is not a simple fraction. It can be some
arbitrary fraction.
Yeah.
And that's completely, so I think it brings to a very interesting point, and it's completely true. You see, recently there has been a lot of discussion about how to prove fractional statistics, which essentially involves such fractional charges. So there's this paper by this Korean gentleman, Sim. So he came up with this idea that if you can take the nu equals to 1 state, which is the Fermi liquid state, and using a gate, if you can generate pulse which has fractional charges, he showed that if you can take 2 of them and braid them, they will actually give rise to fractional statistics. And that we know from bosonization. With mathematics, we know. We never thought that you can do an experiment with it. And he made this proposal, and I think some French groups are really trying to do this. So yes, you are right. Each of these is fractional, and they even have fractional statistics if you could kind of make two of them and start breeding them. Yeah. Yes, how far and how can you really exchange them and so on. So that's, yeah. You're asking how far in an experiment? Yeah, and so that's what I'm saying, that this time between them is not something, it is not stochastic. Can I make them large? I've never tried it. So it's an interesting question. I think so what parameters will optimize it? I don't know. I've never tried doing that. It could be interesting, yes.
So yeah, maybe we can continue the discussion later.
Thank you.
So let's thank the speaker again.